Welcome to Train Signal. You're watching a lesson on processors. Now, when we talk about processors, I'd mentioned in a previous lesson, in the motherboards lesson, that this thing called the CPU, right, the central processing unit, and I said, or what's more simply referred to as a processor. Well, that's what we're going to talk about here. And we also talked about how the processor is kind of like the brains of the computer, right? If we're going to analogize it to human, right, we were saying that the processor is the brains and the motherboard was the heart. So here we're going to talk about the brains. So that's where all the computations take place, right? Or all the processing takes place, right? The processing of information. All right, so that's what this lesson is going to be all about. Now, here's the thing. I will tell you that this information is not always the most exciting of information. And the reason why, if you think about it, well, teaching you how a processor works is kind of like teaching you how a brain works. And for most people, that's not the most exciting information. I suppose unless you're a brain surgeon, right, then you find it very exciting. So if you are coming into this formally as a brain surgeon, or maybe you're currently a brain surgeon and you just want to learn how computers work, well, then this is the exciting information. But for most people, it's not the most exciting, so I'm going to try to keep this kind of short and to the point so that we can move along. It's kind of necessary information, but I don't want to have it long and boring. So first, let's talk about the processor architecture. And the first thing in this architecture that I want to show you, and I'm kind of jumping the gun here a little bit. This is probably something I should show you 3 or 4 more slides in, but I want to talk to you about this right here, right now, because what we have here in this operation is we have something called a cycle. And this term cycle is very important. And understanding that a processor works in cycles is very important, because part of what we are going to talk about later on in this lesson is we'll talk about the speeds of processors. And that's probably the part that you care about the most, right? You want to know what processor to get, and when you're looking at the specs, you're looking at the speed of the processor. You want to know what that means, right? That's all related to cycles. Okay, the speed is how many cycles it has the ability to process each second. Okay, so we'll come back to that, but let's talk about this cycle here. Okay, this cycle starts off with, first we have something called fetch. Okay, and the fetch part of the cycle is where the processor will fetch or get data, and to be specific, we're kind of pulling that data from something called the external data bus. That's why I said I'm jumping the gun a little bit. We haven't looked at the diagrams. These are real fun diagrams, by the way. Looking at diagrams to see what this external data bus is. But we'll just say that we already learned what a bus was with the motherboards lesson. So we're going to say that the external data bus is just that. It's where information travels in and out of the processor. Okay, so we go ahead and we fetch the data. And with that, we then figure out in the decode part of the cycle here, what type of command needs to be executed. Okay, so there's a certain set of built-in instruction sets or operational codes. Okay, these are commands that can be implemented by the processor. We have to figure out what type of command needs to be executed. And then, of course, once we figure out the type of command that needs to be executed, well, that takes us to the next step here, which is actually execute the command, right? So we need to go ahead and execute the command, or what we could say is perform the appropriate calculation, right? Because that's what's going on in the processor. We're processing all these calculations. And then we take those results and we store, and even though it's called store, we store the results, but we don't necessarily store them in the processor itself. They get stored elsewhere, so we go ahead and send that data back out onto the external data bus. So we send it back to whatever device it is that we were communicating with. Okay, so that's a cycle. And when we talk about this particular cycle, and it sounds like, well, okay, that's something, right? That's a significant something. I kind of like it because it's tangible. How many of those do you think we can do in a minute? Well, if we think of it from a human perspective, not a lot. But from a computer perspective, and when we talk about, the electronics of this, we're not even talking about how many we can do per minute. We're talking about how many we can do per second. And believe it or not, we can do millions of these per second. Okay, so 1 million of this process right here happens every second in a processor in a computer. Now, you may also remember that we talked about back in the motherboards lesson when I showed what the processor looked like on the motherboard. We actually couldn't see the processor, right? Well, what we ended up seeing was something I called a heat sink and a fan, right? We talked about for having to cool the processor. Well, the reason we have to cool it is because, well, think about it. If it's doing millions of these things per second, it's going to get quite hot. Okay, but we'll come back to that later on in this lesson when we talk about the cooling aspect. Here's where we get to some of the fun diagrams, okay, and try to kind of simplify this diagram as much as possible. But basically, if you picture the CPU just as you see here, and it's the gray area is, we'll say, the actual, that chip that you see on the motherboard. What's going on inside that chip is all these different components, okay? We have an input-output unit, which of course is what allows for the data and instructions that are going to come in and go out. And you'll notice here we have the North Bridge. We learned about North Bridge in the motherboards lesson, okay? And connecting to that North Bridge is your external or front side bus, okay? So that's where data travels in and out of the processor. We have a control unit, which is what manages the activity inside the processor itself. We have ALUs. ALU stands for the Arithmetic Logic Unit, which is managing the calculations that are taking place inside of the processor. There's memory that we have inside the processor itself. We have registers, which work a lot like RAM. Matter of fact, both the registers and the cache are both a form of RAM. Now, RAM is something that we haven't covered yet. That's coming up in the next lesson. But basically, it's a form of temporary memory where things can be stored while other things are being calculated in the processor. And then, of course, we have the internal bus. Right? I talked about the external data bus. Well, now we have the internal data bus, which is the circuitry that allows data to travel internally, inside of the processor and get from each of these components to the other components within the processor itself. Okay, and again, the bus, just like we learned with motherboards, it's a bunch of wires and circuitry that allows these data pulses, really is what they are. They're electrical pulses to travel. Now, I mentioned cash, right? Not the kind of cash as in money that you go and you spend and buy things. But no, this cache is C-A-C-H-E, and it's a form of memory. And I will tell you that it is a form of very fast memory. And I know, again, some of this is kind of difficult to learn sometimes because we have to jump around. One of the things I can tell you, and when I first started teaching A+, and this goes back probably about 15 years ago, one of the things I had to learn was you want to teach kind of everything at once. And you can't teach everything at once. We have to learn things one at a time. And the problem is that in order to learn A, we have to understand B, and in order to learn B, we have to understand A. That makes for an interesting challenge. So I will tell you that when it comes to processors and when it comes to memory, well, there's a lot of things about these two particular subjects that, well, they kind of complement each other. Okay, and they work hand in hand with one another. And so, yes, I can't teach memory until I've taught you about the processor, and I can't teach you the processor until I taught you memory. So if any of this is confusing, hopefully after you've watched all the lessons, things start coming together. And if need be, this is kind of the luxury of where you can go back and forth and re-watch lessons again. But anyway, cache is a form of memory. It's a form of very fast memory. And we have different levels of this cache. First kind that we have is something called L1 or level 1 cache. And this is actual on-chip or what's sometimes called on-die memory. Okay, this is actual memory that is truly on the CPU chip itself. It is the fastest memory that there is. Okay, because it doesn't have to travel along any form of bus itself. It's right there, built right in there with the processor. Whereas we have L2 and L3 cache, which is slower than L1, okay, but still, and I will tell you, actually, I'm going to take this a step further. L2 is slower than L1, L3 is slower than L2, and it's considered to be what's called off die, okay, which means it's not necessarily on the chip itself, but it's still part of the processing unit as a whole. And so therefore it's still going to be faster because it only has to travel through the internal bus. It doesn't have to go through the external bus like the actual main memory or RAM. Okay, so L2 and L3 cache are still faster than RAM. Now, again, if we kind of go back to the old days and we go to the old processors, there were processors that existed certainly without any L3 cache, and even without L2 or very minimal amounts of L2 cache. So these caches were a way of helping to speed up the processing power on a computer. Now, we don't think of it a whole lot. In today's world, it's just kind of assumed. All processors have this because in today's world and today's needs, today's processing needs, well, we would be crazy to try to use a processor without L2 and L3 cache. Okay, if we were just doing everything from RAM, okay, our main memory, and by the way, RAM stands for Random Access Memory, just in case you were curious, sometimes people will ask, what do the letters stand for? But we'll talk about it in more detail. It has a lesson of its own. But because it has to travel through that external bus, in and out of the processor, it's just not going to be as fast. Now, speaking of fast, right? Speaking of, how fast is a processor? This is probably the number one question that people will ask about when it comes to processors is, I want a fast processor. And I will tell you that, again, in today's world, there's a number of varieties of processors that are out there, a number of different flavors. And I will tell you there's different websites that you can go to that will tell you how a certain processor rates against another processor. And the reason why is because the literal technological aspects that get advertised don't necessarily mean that the processor is going to perform as well as maybe another processor that, the literal technical specs are not as good. And that's where it gets very confusing. But what you need to understand, first and foremost, going into all this, is those literals. Okay, you have to know the actual, terminology and what it means. So when we talk about processor speed, we're talking about the actual internal speed of the central processing unit. And it is measured in something called hertz, okay, which is just Hz. And a hertz is a cycle. Right? Okay, so this is where it all, comes back to that first slide that I was showing that I said I kind of jumped the gun, but I wanted to have it out there. It's the cycle, or a hertz is the number of cycles. Now, this speed, or these cycles, is synchronized by something called a clock or a crystal inside the processor. Okay, so that's how many cycles we can do. And we also have another type of speed, which is something called the bus speed, which has to do with the speed of that front side bus or that external data bus, right? So we have the speed of the internal cycles, but then we also have the speed of the bus to be able to transmit data inside and outside of the processor. Now, a couple of other terms that you should be familiar with. We have something called overclocking. That means that you are running the CPU at a higher than recommended speed. Okay, so in the BIOS, which is something that we will learn about in another lesson, in the BIOS, you can adjust certain CPUs. You can adjust their clock settings or that crystal setting, right? That's synchronizing how many hertz, how many cycles you can do per second. You can actually go faster than what is recommended. Now, what do you risk by going faster than recommended? Well, you risk overheating, potentially. Matter of fact, the illustration I have on the screen where I'm showing some cars, you'll notice that one car, is a sports car, and the other one's more of like a family car. So one's probably going to be made to go faster than the other. And with each of the engines that are in those cars, if you were to go faster than the recommended speed. So here we could say, like, we have a speed limit, right? Speed limit 55 miles per hour. That's how fast you should go on the road. You go faster than that, well, you risk getting a ticket. And if you go way faster than that, you may risk overheating or blowing up the engine. Well, processors have that same recommended limit, okay? So maybe it'll be 2 gigahertz, okay, which would be like 2 billion cycles per second, okay? And if you go faster than that, that's overclocking. We have something called dynamic frequency scaling, which is also known as CPU throttling, which is where you can automatically change the speed or the frequency. And this is a great way to speed up and slow down the processor dynamically as needed to help conserve energy and reduce heat. Okay, help keep from overheating. So one typical place that you might find this would be, well, on your portable computing devices, like a laptop. Okay, because that is a device that needs power conservation because very often it's being run on a battery. And then, of course, the heat aspect of it is also important because very often these devices you're actually holding in your hands, or they don't even want us to call it a laptop anymore because they don't want you to put it on your lap because it does get hot. But realistically, it is on your lap, and you don't want it to get too hot. Okay. The other issue is even beyond the fact that you're holding it, or it might be hot to the touch, is keeping in mind that when you have these smaller portable devices, the ability to ventilate and get cooling to blow through, there's not as much. Okay, when you have a big desktop computer, you can do all kinds of crazy stuff with big fans and water cooled systems, but with a portable device you have smaller fans, so you need to make sure that you keep the heat reduced. I also want you to keep in mind that there is kind of a difference between the actual speed of a processor and the theoretical speed of the processor. And this is where, again, it gets tricky. There's so many factors involved, and why sometimes you got to go out to some of these various ratings websites to see which processors are actually performing better than others, or sometimes it'll be they perform better than others in certain scenarios. Okay, but the actual speed itself is measured by applying the clock multiplier to the front side bus speed. So an example might be a processor that is listed as running at 3200 megahertz or 3.2 gigahertz might be using a 400 megahertz front side bus and an 8 times clock multiplier. Okay, and that's how they get to the 3.2 gigahertz, right? You have a 400 megahertz front side bus, right? That's the speed that you can actually have data travel in and out, and it has an 8 times clock multiplier. You end up with a 3200 megahertz or 3.2 gigahertz processor, right? It's like the advertised speed that you'll see. The theoretical speed is a product of that front side bus clock speed along with the width of the data bus. Keep in mind, we talked about this a little bit on the motherboards lesson, and we'll talk about it more here in just a moment. We talk about the width of the data bus itself and the number of data transfers per clock cycle. Okay, so things don't always work at the exact literal speeds that are listed. Now, when we talk about processor width, this is the actual size of the highway. That's the analogy I've always liked to use. I used it in the motherboard lesson, and I'll use it again here now. Okay, it's the actual width. It's like the number of wires, the amount of data that can travel in parallel with other data. Now, I will tell you that there are 2 common widths that are available in today's processors. We have 32-bit processors and we have 64-bit processors. And one thing I want to point out to you real fast here, this is a quick little side note, a little bit of a history lesson here. On the left here we have 32-bit, and next to it it says x86. And then on the right we have 64-bit, and it says x64. Now this is a question I get asked all the time. It makes sense why x64 means 64-bit, right? But why the heck do we say x86 to represent 32-bit? People have racked their brains trying to do mathematical formulas, all kinds of stuff, trying to figure out how does the 32 and 86, how do they relate to one another? It just doesn't make sense. Well, the reason that we refer to our 32-bit processors as x86 processors has to do with, if we go way back to some of the original Intel processors. Okay, I mean, technically, if you go back way, way back, we can go even before the 86 brand of processors. Okay, but if you go back to the 80s and the 90s, you may recall that there were processors called the 286 processor and the 386 processor and the 486 processor. Okay, so depending on how old you are and how long you've been familiar with computing technology terms, I mean, even as an end user, right, just out buying a computer. And I will tell you, back in the days of like the 286, I was not working in this business professionally. I was just an end user. I was buying a computer. Okay, and so that's where the 86 comes from. The X is like the variable, right? X86, 286, 386, 486. Matter of fact, the processor that came after the 486 was something called the Pentium. And a lot of people are like, well, where'd that name come from? Hey, maybe that's a fun name to say, but what does the word Pentium actually mean? I mean, why did they name it that? Well, because the next processor was going to be the 586 processor. But it got to the point that from a marketing perspective, it wasn't a very attractive name. So they came up with the name Pentium. Penta for 5. Okay, so we have the Pentium processor. How about that, huh? So that's where the x86 comes from, is the older 32-bit processors were named something 86. Now, let's reel it back into the technical specs. One thing you should know is that when you are working with an x86 or a 32-bit processor, the most amount of RAM that processor can associate with and can process and address is 4 gigs of memory. Okay, that's it. You were maxed out at 4 gig. Now, for many years, that was a huge number. I mean, back in the day, we used to talk about how many kilobytes of RAM. And then it was exciting when we got to how many megabytes of RAM. But considering, a gigabyte of RAM is 1,000 megabytes, and, we were looking at systems that had 1 megabyte of RAM, 2 megabytes of RAM, 4 megabytes of RAM, getting up to 4,000 megabytes of RAM, which is 4 gigabytes of RAM. Well, that was going to be way out into the future somewhere. Well, not so much, because we hit that quite a few years back. I'd say, probably about 10 years ago. We were even further back if you really want to talk about mega systems. But I would say a comfortable 10 years ago, we were already, commonplace. Even regular PC users, especially gamers, they were looking to exceed past that 4 gigabyte of RAM maximum. And so that's where we had the need to move to the 64-bit processors, which can actually address 16 exabytes of RAM. That's right, you heard me, exabytes. Now, if you're not familiar with all of the different terminology, and we'll get to this in a later lesson, but I can tell you that, there's 8 bits in a byte. Okay, so each piece of data, right, every 1 or 0 is a bit. There's 8 of those that make up a byte. A kilobyte is 1,000 bytes. 1,000 kilobytes is a megabyte. Okay, so we could say 1,000,000 bytes is a megabyte. Now, by the way, it's not actually 1,000. It's technically 1,024. We just use 1,000 to keep it kind of simple to think about. But 1,000 megabytes is then a gigabyte. Now, those are numbers that most people are pretty familiar with. But when we go up from gigabytes, there's one more that people are very familiar with in today's world, and that is the terabyte. Right? 1,000 gigabytes is a terabyte. And that's because terabyte hard drives are very common right now. But if we go up from the terabyte, 1,000 terabytes is not an exabyte. It's actually a petabyte. 1,000 petabytes is then finally an exabyte. Okay, so when you want to talk about 16 exabytes of RAM, we once again are in a day and age where we're looking at that being well out into the future. But don't get too excited, because as we've seen with technology in the past, the future gets here a lot faster than we expect it to. All right, so it looks like it's going to be way out in the future, but heck, I might be talking to you 10 years from now saying that we're at that 16 exabyte maximum and we need to go to something else. Who knows? All right, so speaking of maximums, right? One other maximum that we have is we have an issue where processors can only process so fast, right? In other words, the actual cycles, how many times it can process a cycle per second, there is an actual pretty finite maximum that we've hit. It's somewhere in that 4 gigahertz region. Okay, we just don't have the technology to figure out a way to make it move faster. So we have to find another way to make our processors faster. And one way of making processors faster, one creative way, was something called threading. Okay, the original processors did single threading. Okay, basically in RAM, right? So out in the RAM, we had data for a task, and we'd have data for a second task. And what basically had to happen was that the data for the first task would be sent into the processor, it would be processed, and then task 2 data could be sent in. Okay, one thread at a time. Well, we've now come out with something called hyper-threading, or sometimes it's referred to as multi-threading. And it's the idea, it was one of the very first virtualization type ideas. Now, don't get this confused with the type of virtualization that we're going to continue talking about, where we have virtual machines and things like that. But it was almost like virtualizing 2 processors within one physical processor, to where you now could send 2 tasks into the processor at the same time, and it could process them parallel with one another. Okay, it had the ability to multitask and do 2 threads of commands at the same time. Now, there are some catches that go along with hyperthreading. You have to have systems that support it. Okay, you have to have applications that were built to cooperate with it. And again, if you go back in time, in the old days when hyperthreading first came out, there were some issues. Not everything was compatible. In today's world, pretty much everything is equipped to support hyperthreading. But keep in mind, it's still just one actual execution core. Okay, there's only one actual processing core. It just figured out how to multitask more than one process at a time. And I will tell you that part of how this happens is because we find wasted resources. We're going to see that anywhere you hear virtualization technology in any capacity ever referred to, it's because we find that the resources are actually capable of more than what we were asking them to do. Okay, so hyperthreading gave us the ability to better utilize the resources by virtually making it seem as though you had 2 processors, even though it was really one just multitasking. If we really want to speed things up, however, we need to move to actual multiple cores. Okay, so here we have the idea of, we have just our regular old processor, right? We already saw this where we have our single core where things can be processed. We've seen a diagram like this before. A multiple core processor, right? You hear about like dual core processors and quad core processors. Essentially, this is the idea of building 2 processors into one chip, right? So it's being sold as one physical component, but inside that one physical component, there are 2 actual processing cores. And each core has its own dedicated piece of processing resources. What we also can do is, using hyperthreading along with a multiple core processor, each core can now do 2 instructions at once, which means that we can emulate as though we have 4 processors in this dual core scenario. Or in a quad core where we have 4 cores inside the processor, we can do 8 processes at once. So it's like we're emulating having 8 processor cores. You can see this in your system. I know one of the easy ways to see it, I know I see it, is when you use, speaking of virtualization technology, if you use something like Hyper-V or VMware for virtualization, when you go to create a virtual machine, that machine is going to ask you how much of the processor you want to use, and very often there's a drop down saying how many processing cores, or sometimes they'll say processing threads, do you want to allocate to that virtual machine. Okay, that's a real common place where I've seen it. Another place you can go is you can go into the task manager in Windows, and you can see the different threads there as well. But if you had a quad core processor, or an example I can use is the computer that I use here, I actually have dual quad core processors. And what that means is, and I'll tell you what, as long as I've mentioned it, let's kind of jump to this. That means there's actually 2 processors, right? So here's the actual motherboard, and this is what, remember I showed you in the motherboards lesson, and we saw a heat sink and a fan. We couldn't see the processor. Well, this is a picture with the heat sink and fan removed. This is what the actual processor chip looks like. And each of these processors in my computer is a quad-core processor that also supports hyperthreading. So what that means is that each processor has 4 cores. It can hyperthread, which means it emulates 8 cores. And there's 2 of them, so that's 16. So when I go in, I get to actually see what looks like I have 16 processors in my computer. And that's how I can run so many different things on my computer when I'm creating these courses for you. All right, so this is how we can get to multiple cores, is you can actually have multiple processors themselves. And then, another way is within the processors, we now have multiple cores. Now, when it comes to the different socket types, right, we were just looking at what the processor looks like, and that's what's called a socketed processor. There was a point in time where we were using slotted processors, where the processor would look like an expansion card on a motherboard. But most of the processors have gone back now to the socketed type of processor. And I'll tell you what here, there's 2 main manufacturers of processors in today's world, Intel and AMD. So first we have Intel. And Intel processors use what's called an LGA type setup, which stands for Land Grid Array. Okay, that's what type of package it uses. Where basically the underside of the CPU has hundreds of contact points that line up with the socket pins. So what you see on the screen in front of you, you should probably just, study this before you go take the exam, because these are the different types of processor packages that they have. There's LGA 775, 1155, 1156, and 1366. And you'll see here that the LGA 775 was the exclusive server and desktop socket for many years. If you look at what types of processors you have, it's the older ones, right? You have the old Pentium 4, and believe it or not, remember how I talked about 286, 386, 486, and then we moved to the Pentium? Well, to give you an idea how old we're talking about, here we have Pentium 4, which of course was after the Pentium 2, the Pentium 3. Matter of fact, we actually had things in between, like the Pentium MMX. If you go back and look at the history, you'll see there's all sorts of old Pentium processors. In today's modern world, you won't see anything, realistically, anything older than the Pentium 4, a Celeron. There's also something called the Pentium 4 Extreme, the Core 2 Duo, the Core 2 Quad, Xeon, and there are many others because, again, we could go further back in time. We have the LGA 1155, which uses something called Sandy Bridge or Ivy Bridge architecture. And again, I'm not going to get into the details. This is kind of stuff, again, just study and memorize for the exam. It's your core i3, i5, and i7 processors, which are more of what we see in today's processing world. But we do go back to the old Pentiums, Celerons, and Xeons as well. We have the LGA 1156, which is the pre-Sandy Bridge architecture. This is not that old, though, because we're still talking about the core i3, 5, 7, Pentium, Celeron, and Xeon. Okay, so the only difference between the 1155 and 56 is Sandy Bridge or not Sandy Bridge. Then we have the LGA 1366, which is what we used for the original i7 processors. It has core i7, Xeon, Celeron. Okay, so some of the original processors that fall into that series. There's not a lot I can tell you here. I mean, this is just kind of a grid, so to speak. I know I didn't format it here in the form of a grid, but I might as well have. It's a form of a grid just to memorize for the exam. Now, one other thing that I could mention here is if you're wondering about the numbers, why is it LGA 775, 1155, 1150? Where these numbers come from? Well, they have to do with the number of pins. Okay, so the pin count with the processor. Although I do want to caution you. Well, there's a couple of things I want to say here. Number one, I don't know that you ever really need to know the exact pin count of a processor. I mean, I suppose if you're ever looking at a socket and the socket shows a number, well, then that number, again, is going to represent the number of pins, so you want to get a matching processor. But the second thing I want to caution you on is just because these processors may have the actual pin count listed in the name, I don't want you to get thrown off in the future if you see some other processor. And I'll tell you, even as of right now, I don't know that I can speak for every single processor in existence and say that every single one, the number that is tied in with the name represents a pin count. So, again, a little trivial piece of information. Thought I'd throw it out there at you. There is the second manufacturer, however, that I mentioned, and it's called AMD. And AMD, well, they have their own series of chipset packages. They actually use something called PGA, which is a pin grid array, and that's where you actually have these pins that are on the underside of a processor, and they align with the holes in the sockets. When using an AMD processor, when using a PGA-based processor, and I will tell you some of the old Intel processors also use these PGAs. I'll tell you what, it was so easy to bend these pins. I mean, it took nothing for these pins to accidentally get bent. So you had to be really careful when you line up the pins with the holes and put it into the actual motherboard. Now, I am going to have a demonstration for you in a later lesson where I go through and show you what this stuff all looks like and show you how to build a computer. And I'll show you how these sockets and the pins and how they're really sensitive, and you got to be really careful with them. But again, I'm not going to go through this whole grid here, but you have this whole different socket type, okay, with the 940, AM2, AM2+, AM3, AM3+, which, I will tell you, the 940, AM2, and AM2+ all had 940 pins. The AM3 has 941. The AM3 Plus has 942. We had the FMI, which only had 905 pins, and the F series, which have 1,207 pins. Yay. Okay, I'm just kind of throwing out trivial information. Okay, I just want to make sure that you just kind of have this information in case it's thrown at you on an exam. Now, the last piece that we want to talk about, and I'll wrap things up here, is cooling. And this is real simple. I mentioned that, we have millions and billions of cycles per second taking place inside of these little chips. So they get quite hot. And if they get too hot, well, then they just completely burn up and cease to exist. So we have to have some form of cooling. Now, the most common form of cooling that you'll see in today's computers, well, even in old computers, is using this thing called a heat sink, okay, which is the metallic object, which is an object that sits on top of the processor and is designed to draw heat away from the processor. Okay, that's what the idea of the heat sink is. It's designed to pull that heat up and away from the processor. And the fan that you attach to the top of the heat sink will then blow that heat further away. And to be more specific, it will then coordinate with other fans inside of the box, right? The actual box that you build your computer inside of, all the circuit boards and everything are inside of. That box will also have fans to help airflow keep flowing through and the heat stays away from the processor. By the way, this is a big mistake that I've seen a lot of people make, and that is that they will install the fan backwards. When this fan spins, it blows air, right? That's what a fan does. And what people will do is they will plug in the fan to see which way air is flowing. Or sometimes the fans will actually list, they'll actually have a little arrow on them that actually says airflow goes this way. And what people think about is they think about it as a human. If I want to be cooled off, what do? I take a fan and I blow it on me, right? I want that breeze blowing on me, and that cools me off. Well, you have to understand that humans work different than processors. Okay, humans sweat, and so when you blow air onto that sweat, you are cooled. Whereas with the idea of the processor here, it doesn't sweat. So blowing the air on it, it may cool it a little bit. Creating a breeze on something may cool it a little bit. But what you really want is not to have the fan blowing down onto the processor. You want the fan blowing the heat away from the processor, right? The heat's coming up through the heatsink. You want to blow it away from the processor. So besides the heatsink and fan, something else that you should be using with today's processors and today's computers is something called a thermal paste. Now, I have it illustrated for you here on the right in the form of, you'll see it's just called heat sink compound. Okay, it's basically just a paste that you put on the top of the processor before you put the heat sink down on it. And really all it is it's this compound or this paste that is designed to help, again, induce the flow of heat up into the heatsink. Okay? Again, in the old days, we used to just use a heatsink and fan. We didn't worry about the paste. Now the paste is much more important. Okay, so these three things kind of go together. But there is another form of cooling, and that is liquid cooling. Right? I mean, I already mentioned that humans, we cool by sweating, right? By having liquid on us. Well, the idea behind liquid cooling is that you will have some form of liquid. It could be water. And what's going to happen is you're going to run that liquid through a metal block that sits on top of the processor that's, again, absorbing the heat, right? So what's going to happen is the processor is getting hot. You have this metal block that's on top of the processor that is going to be like the heat sink. It's going to absorb the heat. The liquid, so we'll say the water, will get hot, right? This block will heat the liquid. So the liquid then needs to run out of the block and into some form of a cooling system, which you'll notice the illustration of what I have here would be fans, right? You have fans that are cooling the liquid so that the cool liquid could then feed back into the metal block. So you basically have this constant flow of liquid. So the liquid goes in, it gets hot, it comes out, it gets cooled off, it goes in, it gets hot, it goes out, it gets cooled off. It always looks really super cool. It's a great way to show off to people, make them look like you have a really cool computer. And I guess that's pun intended, right? It's a cool computer, because we could say cool as in neat, or we could say cool as in, well, it's cool, it's cold, right? It's keeping the processor cool. So anyway, that's how we cool the processors, and that does take us to the end of this lesson. Okay, so I think I probably went a little longer than I would have liked to have. I told you this is not the most exciting material, but it's important material, so I had to get through all of it. And you really want to understand the absolute basics of how the processor works, or how the brains work in a computer, so that you can know what makes everything happen, what makes it that when you ask things to happen on a computer, they actually happen. All right, so that's it. I thank you for watching, and I will see you in the next lesson.